Hello, everyone. Welcome to this seminar. Today, I will introduce Tensorboard, a toolkit that comes with Tensorflow. You know, Tensorflow and PyTorch are the two most popular deep learning platforms. Tensorflow provides not only the API for users to build neural network models, but also a collection of tools that can be used to visualize the training process, debug anomalies, and profile the training performance. So since it is not possible to cover all the tools in detail within a 1 hour time frame, so the goal of this seminar is to focus only on the debugger and the profiler. So I will start with a brief overview of Tensorboard and introduce how to launch it on our clusters. Then I will use several examples to walk through the debugging and profiling processes step by step. So you can find a lot of related material on the TensorFlow website. At Computer Canada, we have a wiki page about using TensorFlow and the Tensorboard on our cluster. Here, I also include a link for you to download all the examples that I'm using in this seminar so that you can play with them afterwards. So I'm gonna use MNIST and Cypher 10 in this seminar. MNIST, probably most of you already know, is a dataset of handwritten digits images. Each sample is a 28 by 28 grayscale image. And in your Python code, you can load such a standard datasets through either the Keras interface or the TensorFlow datasets interface. Each of them has its own default location to look for the datasets. If the dataset does not exist in the default location, it will download it from the internet. However, our compute node do not have internet access. So you have to pre-download the dataset on the login node because our login node has the internet access. So you only need to do this once, all right? One thing that I would like to mention is that we also have, we also maintain a data repository on Gram. It's under, it's located at /datashare, where we maintain a lot of commonly used datasets there. Such as MNIST, Cypher 10, Cypher 100, also the larger one like ImageNet. And if the dataset you are going to use is already in the repository, then it's easier. So you simply need to create a symbolic link in the default location of the data loading function, and to let it point to the one of the data file in the repository. That's all. Also, as I mentioned, there are two interfaces that you can use to load data. You can check the catalog of each method to see what datasets can be loaded through each interface. here are the typical steps to start a Tensorboard on our cluster. So first, you need to initiate an interactive session on our cluster. And then once it's granted, you are landed on one of our compute node. Normally, a GPU node is preferred because a GPU has advantages for neural network training. So once you landed on a compute node with GPU, you need load required modules. For example, if you want to use a GPU, you need to load CUDA, cuDNN. You also need to activate your virtual environment where Tensorflow and other required packages are installed. After that, you run your Python code, which output logging information into some directory. And after that, you launch a Tensorboard by specifying where to find the logging information. You are ready to go, okay? Then you need to make a connection between your local computer and the remote compute node through a port 6006. Once the connection is created, you can launch a browser on your local computer, and then you can view the Tensorboard that is running remotely on a compute node. Okay, this is the process. So how to make your Python code to output logging information? There are several ways, but the simplest way is to use a Keras interface. Basically, you need to create a Tensorboard callback in which you tell it where you want the logging information go to. And plus, there's some other optional arguments that you can pass in. Then you hook up the callback with your training. So basically, you pass it to model fit. So that's the typical way of doing it. So now let's take a look. So let me do an example. So first of all, let me introduce. I already logged on Graham, and I started interactive session by asking 16 gig memory, 4 CPU cores, and a GPU. That's all. Now I'm landed on Graham 874. Okay, so here I would do. So once I log on here, I go to the directory that contains my source code. Okay, here it is. So first thing first, I'm gonna activate my virtual environment and load all the required modules. So if you do a module list, you can see here I load CUDA, cuDNN. I'm also load the SciPy stack. And there should be Python. Okay, here Python 3.8 is loaded. And let's check what I installed in my virtual environment. I do a pip list. You can see a Tensorflow, Tensorboard, and also Tensorflow data sets and some other things are installed there. Okay, so I'm ready to go. So let's do a list. So I want to mention that because I already give you the link to download those examples, I already created a read file, so you can check the instruction in the read file to help you to do the experiment. So basically, let's go to warm up. So this warm up is basically, create a general, just output the general logging information. So let's run it first. So in the meantime, I'm gonna make a connection. It's all right, I think that's it. So you ask me, yes, yes, back. Okay, so I'm done here. That you can see that it's running okay, but when I do a list, you see a new folder, log file. That's where the logging information go to. Let's quickly check the code. It's because it's not so complicated at all. Basically, I load the data and create a model through the Keras interface, and then I compile it. And after that, this part you should pay attention. I created the callback, the login directory. I use log / the current date and time. And then finally, once I hook up the callback and put it here to hook it up with the training. So it's very simple. So let's start the Tensorboard. So the Tensorboard, the command is here. So you probably notice the ampersand at the end of the command. That's why I want to run this command in the background. So let's run it. So once this is done, I'm gonna, let's move, sorry. I'm gonna start a local host, give them 6006. So see, it's connected. I see the graph here. So because, like I said, I just want to give you a quick overview. I do not want to spend too much time on each of the tabs. So you can see scalar. On the scalar tab, you can see the performance, because I do 5 epochs training. So you see the accuracy goes up, the loss goes down, right? So as I go from epoch 0 to epoch 4, okay? So it's makes sense. And also graphs. This is the graph of the neural network. So it looks strange to you, unfamiliar probably. That's because it's used the low-level, operation to represent the graph. So it's hard to understand. So the way you can change it is you choose the tag from default to Keras. Then you can create a conceptual graph, which is much easier to understand. So double-click this. You see that the first is a dense layer, from the bottom, flatten dense layer, and then drop out and the dense layer. So if let's check the code again, we have flatten dense, drop out dense. So that's exactly what we see here. So it's conceptually. So here, distribution shows the training parameters, how they change along time, and also histograms of those, the training parameters, training variables, whatever you prefer to call them. All right, so that's it. So so here we have a brief overview of the of the how to use it on our cluster. And now let's move on to the next topic, the main topic, which is the debugger. People may wonder why we need a debugger, what happens, why those anomalies could happen. So you can consider a neural network as a computational graph. And such a graph can be decomposed to many basic operations, or also called ops. So some of the ops could lead to either infinity or none or other anomalies. For example, when you do logarithm operation, if x equals 0, you will get infinity. If you do a square root operation on x, if x is less than 0, you end up with none. So that's the potential dangers, okay? So how to detect such anomalies? TensorFlow provides 2 ways. One is using, enable check numerics. And when you enable check numerics, it will output errors whenever it finds anomalies like infinity or none. Another way is to dump the debug information into a directory, and so later on you can load the debug information into Tensorboard to check. So I will use the second method. So let's do it again. So here I have 2 examples. So let's run the first example. I think that's it. So when it's running, probably I take the time, to check the code. So I'm using this one, training. Let's go to debug. I'm not sure it's finished or not. Okay, it's finished. Okay. But still, I want to show the code on this tab. So it's debug MNIST v2. So I do not want to jump to detail because this code is a little bit long, although it just creates a very simple neural network. It's 2 dense layers. It only has 2 dense layers. But the code is a bit long. The reason for that is I'm using the low-level API of TensorFlow instead of the high-level API. So that's why it's a bit long. And let's go back to the execution terminal. You probably notice something not right. So you see I run totally 10 steps. You can see the first step is a little bit above expectation, but then after that you see the accuracy is below 0.1. You know, the random guess of a digit out of 10 choices is 0.1, but it's almost around there. So it's something wrong. So what happens? Because when we run the code in debug mode, we got the debug information in the log directory. So let's take a look how I did that. So basically, it's very simple. Probably I showed it in my slide as well. So basically, you see, you use enable dumpling debug information, specify where you're gonna dump it. And also, if you want the full information, you just pass the tensor debug mode as a full health. So you can get every information there. So let's take a look. how to do that. Let's go back here. Because the current TensorFlow is still running, but it's pointing to another directory, so we need to kill it. Sorry. So first kill it first. Then I'm gonna run this one again. But this one, but this time, because I'm launched it from a new directory in the debugger directory, so it points to the log directory in the debug. So it is this one. So let's take a look here. Go to the Tensorboard. So I'm gonna refresh it. Okay, so once you see this one, you see, okay, something wrong. No, it's not wrong, because I probably noticed that here the login node doesn't contain the normal Tensorboard login information. It only contains the debug information. So what you need to do is click here and find the debug. Okay, here, debugger. Now, why is the data is not available? It probably takes some time. Sometimes takes some time, give it some time. Let's check again to see anything wrong. No, I don't see anything wrong. Let's try again. I see sometimes it need time to refresh. Still take some time. Should work. Let me see if I did anything wrong. Check the PS. Yeah, it's there. Logging. The log data is here. Log and debug. Yes, log and debug. That should. Oh, sorry. My fault. I see what's going on here. So I'm gonna kill the Tensorboard again. Sorry for my stupidity. So the directory should be end debug. Okay, this one should be okay. Let me check again. Tensorboard should be good now. Okay, it should be good now. So let's refresh again. Yeah, so now I see everything is loaded up on my browser. You can see that in the debugger toolkit, you can see that it already found none or infinity occurrence 499 times. So where are they? You just click on it. Once you click on it, you see the pink color point here. Okay, then you see, oh, because the problem is you can see a 7 negative infinity occurred as a result of log computation. You click on the logarithm, then you see the input of the log is probs. Probs is here, and the input, it is the input here, okay? And also very useful is the stack trace, the calling stack. So you can see that once you click here, you can see the location. Okay, probably I should do this. To this one. It shows the where the calling stack where the problem happens. So once you have the first 7 infinity, the next multiplication will get 7 nines, and after that it's just exploding the arrows. So now, because we know the problem is from the log, let's check the code again, and we can see we can easily locate the problem. Basically, you just type log. So the log operation here is that you do what I do here is I'm trying to calculate the loss function. The loss is basically the categorical cross entropy, but instead of just call that function, I do it manually, and this is where the problem occurred. So this is the function. The whole function is from here to here. Oh, sorry. From here to here, and the input to the function is the probability that that produced by your current model, and this is the label or the ground truth. So for some reason, the probability becomes 0. It is possible if the model is 100% certain about the, output, it's a certain, say it's not a digit 1 or digit 2, so it could happen, but such a if it's 0, it causes the log generate infinity. That's the problem. A fix or a solution for this problem is, let me see, you basically, instead of doing just log, you add a small number. So basically I comment out uncomment this and comment out that. So you see, instead of just doing the I do clip, basically I clip the probability, make sure it is between 1 and a very small number, one very small positive number. So that will make my prob safe for the logarithm operation. So that's the solution. So let's save it. And okay, so and let's run it again. Let's run it again. Oh, sorry. Oh, sorry, I cannot run this. I shouldn't run this. Fine. Sorry. Okay, I'm running it again. So now you see the accuracy makes sense. It's basically keep growing, and you can say that this problem has been solved. To double check, you can go back to your web browser and refresh. And this time, oh sorry, I think it's cache the error. But anyway, what you need to do is I think I know what's going on here. Is cache so basically you need to remove the log. Sorry. The log file again. Yeah, I need to remove this one. And yes, and I need to kill the I need to kill the Tensorboard. For some reason, it cached it, and kill it completely. And if I do Python again, give it a few seconds. All right, so let's PS. So let's do Tensorboard fast force. Do it again. Let me refresh this one. Okay, give it a few seconds. Again. Okay, so now I'm in debugger. So now you won't see any alerts there. So it's fine now. Okay. And if you're still not convinced, if later on, if you do exercise, you can, for example, here, why is it? Anyway, never mind. Debug. You can increase the number of iterations by doing more iteration. You can see the number of accuracy will, instead of I think the highest right now is 0.3 something, then it will close to 90%. I'll leave that for you to try. Okay, so at this point, you may argue that why we need to use the low-level API is so error-prone. With low API, you have more flexibility to build your model, but that requires more advanced skills. Of course, it's easier to use a high-level API like a Keras, but even with Keras, sometimes it still can cause some anomalies. That's our second example. Let's quickly first let's run. Let me do how to run it. So basically, I just do this: run Python. I do debug. I say true, and let it run. And here is the code. So with a higher level API, you can see that I created a fairly complicated convolutional neural networks, at least much more complicated than the previous example. I only take a few lines of code to create the model. It's so efficient with high-level APIs. And you may wonder where the example comes from. Actually, it comes from our wiki page. If you check the Commit Canada wiki page, search for TensorFlow, you can find the code. And previously, actually, this is the previous, examples. Let me see. You already found the problem. You see here, the loss is none already. And you may wonder why. The reason is, if you look at the code, you won't see any troublesome operations. It's just normal. For example, convolution operation actually implement as matrix multiplications, and activation is safe. Nothing. Polling is also safe. You do not see any thing like square root or something like that. What happens? Although there's sparse categorical cross entropy inside, it has logarithms, but it already take care of the logarithm by clipping between zero, not between zero, between a small number and one. I think it's already take care of that, so it's safe. But then why? Why still we have problem? So let's give it a check. Give it a check. So like I mentioned earlier, I have to kill the Tensorboard process. And then I need to check where I am. So the new output is here. So what I need to do is I copy this one, but I need to change debugger to debugger carers. I think that's all I need to do. Should be good. Okay, so let's go back to here. Refresh. Okay. Take some time to load. So here you can see it's already found 1,000 occurrences of anomalies. So if you click on this one, you see, wow, there's a lot. You see, you have a lot of none and a lot of negative infinity. What's going on here? You see, it's generated by convolution, 2D convolutional operation. As I mentioned, the 2D operation is just a matrix multiplication. Nothing could, lead to such anomaly. What happens? The reason is when you do a neural network training, it's not just a one path, not just a forward path. It also does the backwards path to calculate the gradient. And whenever you see something you cannot figure out, in this case, it's because some anomaly happened in the back propagation process. That means it's not stable. Instead of converging on the result, it's exploding. So the gradient is not calculated, not stable. So let's check the code. What happens here? Okay. Oh, sorry. Oh, yeah. So here you can see that the only thing that you need to pay attention is the learning rate in this case. In this case, I use 0.1. And that was the value in the old wiki page. And I think in the old version of TensorFlow, it was able to converge, but for the later implementation of TensorFlow, I mean the new version of TensorFlow, something changed inside, it become unstable. But anyway, the whole structure is not that stable, so be careful. So what I'm gonna do is, because I already make it a argument that I can parse, so I don't need to change the code, but when I run it, I can run it in another way. So I can do it this way. So first of all, like I said, I want to kill this because otherwise it will cache the contents. So I killed the Tensorboard. And let's do a list, and I remove the log directory. And after that, let's run the Python code again. Let's check the. So what I need to do is I run this one, and also learning rate equals 0. I make it smaller this time. Let's run it. So now you can see the loss is no longer none. So you can see the loss becomes smaller and smaller. So that's good sign. So let's check the code again to fully understand the concept. So, so here you can see that the normal, if I use debug, that means this one becomes true. So I enable dumping the information as I used to, and then later on, after that, I create the models. If the I check the learning rate, it must be greater than 0. That's just nothing. All right, so yes, okay, one more thing that is here I use the Cypher 10 instead of MNIST. And like I mentioned earlier, I pre-download MNIST, but I didn't pre-download Cypher 10. So what I did is, probably I'll take this time to give you a look. So I do, so the default location is the keras. I think it's datasets. So you can see here is my location. I downloaded MNIST, but for Cypher 10, I didn't download it. I just create a symbolic link to make it point to the correct file in the data repository. So that's what I did. Okay. All right. It's almost finished. Hopefully, so you see the loss becomes 2.3. Although the accuracy is not great, I encourage you after this seminar, if you try the code, increase the epochs number from 2 to some number like 10 or 15, you will get a much higher accuracy. So that means with a lower learning rate, it converts slower, but it becomes stable. So that's conclusion. So let's PS. Let's do it again. So this time, I'm doing this one. Should be good, right? Yeah. So I'm doing this one. Now I'm gonna refresh it. Give it some time. You see, alert is still loading, but I'm sure alert is 0. Just pay attention to this part. Okay, alert is 0, so that means we have fixed the problem. All right, so we have some time. Let's move on to the next topic, which is profiler. Let me do this one. Okay. So the example comes from the Tensorflow official website, from the tutorial, and I haven't changed a single character. So let's run it. The result is a little bit surprising. You will see soon. So I'm gonna kill. Oh, sorry. First, I'm kill this. The Tensorboard. All right, so let's change it to another directory called profiler, do a list. So readme file. So basically, let's quickly check the code. So here you can see that I load in the data, and I think I click here. Yeah, I do not need to change anything. The only thing that I specify is this part. So because here I'm gonna profile the performance of the training of this specific neural network. It contains only 2 dense layers, so very simple, nothing fancy. And why I choose 700 to 720. This is because my batch size is I choose 128, and the training data contains 60,000 samples divided by this one. So each epoch contains about 350 or 60 batches. So I choose 70 is in the middle of second epoch. Okay, that's why I'm doing this. So let's run it. I missed one. You see the during the second iteration, it stopped halfway and then finished. Okay, so let's check. First do the oh sorry, first list. No. Oh, logs. Yeah. So I'm gonna copy this one because I always forgot the details of this one. So instead of fit, I just doing this one should be good enough. Yep. All right. Let's see anything wrong there. No. So let's check. My Tensorboard, I'm gonna refresh it and go here to choose the profile. So now, let's give it a full screen. So now something, unexpected, at least it's different from the results that show on the tutorial, on the Tensorboard tutorial. So on the, if you check the original one, it shows the bottleneck is in the input, which is the color of like a darker salmon color here. But here you see it's not very large one. It's only 60. Sorry, not 6%, 6.3% of time spent on the input pipeline. So if you take overall, the average step time is 3.4. You can see here, and the input only takes like 0.2 milliseconds. So input is not a problem. So what happens? Why the on the Tensorboard it says the input pipeline is the bottleneck? The reason is later on I found that the tutorial hasn't been updated to catch up the new release of Tensorflow or Tensorboard, and I think because here I'm using Tensorflow version 2.8, it already take care of those inefficiency in the pipeline. So to make it to reproduce the problem, I have to cripple it. So let's take a look of the next one. So what I did is to see the note here, I disable it. So how I do that? So I create a configuration by saying that I do not want auto cache. I want disable auto cache, make it a false. Okay. So once I have such a configuration, when I load my data, which is unmissed, I pass the configuration into the load function, say, don't do the auto cache. Okay, that will make the problem show up again. So let's do it one more. So do Python this one. All right. So now we just refresh again. So here you can see that under this tab, I have 2 runs. It automatically pick up the latest one as the current one. So you can from this is time encoded. So the date and the time is 12:52. So here you can see the problem reappeared. So you can see the input takes about 65% of the total time. So the total time is 7.5 milliseconds, and the input takes almost 5 milliseconds. So this is the problem. So how to fix it? Because like I said, 2.8 already set up the reader at the optimum settings. So basically you don't need to do anything. But if you want to correct it, you basically re-enable the caching or prefetching. So the idea is the same. The reason that I'm using this example is I'm gonna tell you, whenever you want to create a pipeline from your own data by using your own methodology, probably you end up of let your pipeline at the end of your input pipeline is a type of Tensorflow data datasets. So with that one, exactly like I have here, I have this one. It's tf.data.datasets. I can do mapping, I can do batching, I can do caching or prefetching, whatever you need to do. I want to mention that mapping is do a transformation. So here I do a very simple normalized transformation. If you take a look of the code here, where is the mapping? Oh, here, just above. So the mapping, the normalization, just execute this one. Basically, I do not do anything to the label, but I just divided the pixel value by 255. By doing that, you actually map the value of the pixel value from 0 to 255 to the range of from 0 to 1. So that's something it's a way to do, and also to make it run more efficiently. You can choose to make the mapping or the transformation running in parallel by specifying multiple threads. So here, the easiest way, for my case, I can specify 4 because I allocated 4 CPU cores. But the safest way suggested is you let TensorFlow decide for you to optimize everything for you. So this is the code. So let's run it again, a new code. I mean, not again, but a new version with the caching or prefetching. So probably I will take this time to go through some basic knowledge of what fetching on or caching means. So let's do this one to go back. Okay, yes. So so here is a typical input pipeline, the components of the pipeline. So first you need to open a data file. Then you started to read a chunk of data into memory. And then you need to probably you need to transform your data. In our example, you see I map the value from 0 to 255 to 0 and 1 range. And after that, you send the batch of data from memory to CPU, and then the CPU do the training job. So the So, so you see the input pipeline is composed of the 4 components. So in the so here I show in the first epoch, you only need to open the data file once, and then read, do the transformation, send it to the GPU, do the training, and after the training is finished, you started reading the next chunk of data and repeat the process. And suppose I only have 3, I only have 3 batches to loop around to complete epoch. But normally the epoch contains a lot of more batches. But here, for illustration purpose, I only show 3. So next, when the next epoch started, because you didn't keep anything in the memory, you need to repeat the process again. By opening the file, reading from disk is really time consuming. What can improve the process is caching. So normally you cache the data after the transformation, after mapping. So you cache the data after mapping in memory. And this is feasible only when the data set is not large. It's small enough to fit into your memory. Okay, so once you keep the memory, keep the batch data in memory, in the second epoch, you do not need to repeat open, read, and map. You just, because the data already available in your memory, you only need to send it to the GPU to let the training start. So that saves a lot of time. And one more thing about is about another strategy is about prefetching. So here you can see in the old fashion, you start reading the next chunk of data after the first training is training on the first data, the batch data is finished. You don't have to wait that long. You actually can short the process. Basically, you can move, make them tighter. By doing this, you can save a lot of time. So that means I can, group read, map, and fetch into one unit is something like this. So basically, you group read, map, and fetch into a group. And once it's ready, you can have training. And when you don't have to wait the training is finished, you can start the read and map and fetch again. That means you overlap the model training and the data preparation. So that's a big gain. And you can make things even better by combining prefetch with the caching that I introduced in the first place. So that is a lot of gain. So I think I run out of time. So I'm gonna stop here. If you have any question, I think you can ask now.